Alright, today we're going to build convolutional neural network to classify images of cats and dogs. But I don't just want to show you how to train a model. My goal is that by the end of this video, you understand why every line of code exists, what every layer does, and how to recognize problems like overfitting. We will start from the raw dataset, prepare the images, build our CNN, train it, and analyze the results. The dataset we will use is the famous dogs vs cats dataset from Kaggle website. Since we're working in Collab, we first need to bring our Kaggle account and download the dataset directly into the Collab environment. So you need to open Kaggle accounts if you don't have and get the data accordingly. Now, after running these lines, let's verify that the images were extracted correctly. If everything worked correctly, as we can see, we have 25,000 images. The dataset is downloaded as one large folder containing all 25,000 images. Technically, we could work with it like this, but it's not a convenient structure for training. Instead, we will organize the data into the format expected by Keras. For train, we open a folder, and inside it, we open a two folder to separate the cats and dogs for validation and test. Also, the same process to open a separate folder and separate the data. This structure makes it much easier to load images automatically during training. For creating folders and copying files, we will use two standard Python libraries, the OS and Shotil. First, we specify where the original images are located. So next, we create a new working directory where our organized dataset will live. Now we create separate folders for the training, validation, and testing dataset. Alright, inside each of these folders, we create one folder for cats and another for dogs. Now we split the dataset into training, validation, and testing sets. For this tutorial, I don't need all 25,000 images. Using fewer images makes training much faster while still allowing us to learn all the important concepts. We will use 1,000 cats plus 1,000 dogs for training, 500 cats plus 500 dogs for validation, and 500 cats and dogs for testing. First, let's copy the training cat images. The remaining copy operations are exactly the same. So we simply change the image indicates and distinction folders for validation, testing, and dog images. So before training any neural network, it's always a good idea to verify that the dataset was created correctly. Let's count how many images exist in each folder. So by printing as we can see that we have 1,000 images for training for each cats and dogs. For validation, we have the 500, and for the test also we have for both of it 500. So if every number matches what we expected, we are ready to build our first CNN. Now it's time to build our first convolutional neural network, or CNN. Before writing any code, let's understand the overall architecture. Our model consists of four convolutional blocks. Each convolutional layer extracts more complex features from the image, while each pooling layer gradually reduces the spatial size of the feature maps. This helps reduce computation and allows the network to focus on the most important information. After the last convolutional layer, we will use a flat layer to convert the three-dimensional feature maps into a one-dimensional vector. This is necessary because dense layers only accept one-dimensional inputs. Finally, we will add a dense layer with 500 dual neurons, followed by an output layer with a single neuron. Since this is a binary classification problem, we only have cats and dogs. The output layer uses a sigmoid activation function. Sigmoid products a probability between 0 and 1, making it neural choices for binary classification. Okay, before training a neural network, I always like inspect the architecture. So the summary function gives us valuable information about every layer. It shows the output shape after each layer, the number of trainable parameters, and how the feature maps change as the image moves through the network. Notice how the number of channels increases from 32 to 64, and finally to 128. As we go deeper into the network, the model learns more abstract and more powerful features. After the last pooling layer, the feature maps are flattened into a single vector before entering the fully connected layers. Finally, our network outputs a single probability representing how confident is that the image belongs to one of the two classes. All right, now that the network architecture is ready, we need to tell Keras how the model should learn. This step is called compiling the model. There are three important choices here. The first one is the loss function. Since our output layer uses a sigmoid activation function, and we have only two classes, the correct loss function is binary cross entropy. If instead we had multiple classes with a softmax output layer, we would use a categorical cross entropy. Next, we choose the optimizer. We will use RMS prop, which is one of the most popular optimizers for training convolutional neural networks. Finally, we will monitor the model's accuracy during training. Now we need to fit images into our neural network. A neural network, we need to fit the images, and the question is why don't we simply load all images into memory? For small datasets, this is possible. However, real-world datasets can contain hundreds of thousands or even a million of images. Loading everything into RAM is often impossible. Instead, Keras provides an elegant solution called image data generator. Rather than loading the entire dataset, it loads only one mini batch at a time and send it to the GPU. Wait until the model finishes processing it and then loads the next mini batch. This makes training much more memory efficient. At the same time, we will normalize every pixel by dividing it by 255 so that pixel values fall between 0 and 1. Now let's create our generators. The follow from directory function automatically scans the folder structure we created earlier. It reads the images, resizes them to 150 to 150, creates mini batches, and automatically assigns labels based on the folder names. Since this is a binary classification problem, we specify class mode to binary. Before training, let's inspect one batch of data. The generator returns two objectives. The first contains the images, the second contains their labels. If we print the labels, we will see 0 and 1. This represents our two classes. We can also check which number corresponds to cats and which corresponds to dogs by looking at train generator class indicates. Now let's inspect the image batch. So the output is the first dimension is the batch size. The next two dimensions are the image height and width. Finally, the last dimension represents the three RGB color channels. Let's verify this one more. Now we're finally ready to train our CNN. Note that we don't specify a batch size here. Uh, that's because the generator already knows the batch size we defined earlier. The generator continuously loads one mini batch, feeds it to the network, and repeated this process until all images have been seen. We will train the model for 30 epochs while evaluating its performance on the validation dataset after every epoch. Now let's do wait the model to be run. All right. The first thing many people look at is the training accuracy. In our case, it reaches almost 98 or near to 99, which sounds excellent. But is our model actually good? Not necessarily. The real test is the validation accuracy. Here we obtain around 73%. This large gap tells us that the model is memorizing the training data instead of learning patterns that generalize to new images. Let's visualize it. Notice how the gap between the training and the validation curves increases after only a few epochs. This is one of the classic signs of overfitting. One of the simplest techniques for reducing overfitting is dropout. Dropout randomly disables a fraction of neurons during training. This prevents the network from relying too heavily on a small set of neurons and encourages it to learn more robust features. Here, we will add a dropout layer with a rate of open 5 before the dense layer and train the model again. Now we have to wait that model to be run. So after running the model, as we can see, plotting, the learning curve again, we can see that dropout improves the validation accuracy compared to the previous model. However, the gap between the training and validation curves is still noticeable. So also dropout helps. Um, it doesn't completely solve the overfitting problem. So the question is how we can handle the overfitting. In the next video, I will go much deeper and we will understand why neural networks overfit, how to recognize overfitting early, and explore more powerful techniques such as data augmentation and other methods that can significantly improve generalization. All right, thanks for watching and see you in the next video.